Okay, and so what did this actor do? There was a large European IT company that had the breach in mid-2013, was hit by this actor, yeah, they compromised a lot of Linux servers in that organizations, and I'm going to be talking a little bit about the motivating intrusion here, but not too much, obviously. Then I'm going to be talking a little bit about the ELF format, because the actor used PLT hooking in this intrusion. So, talking about dynamic linking and what PLT hooks are. And then detecting such PLT hooks with volatility. So, because, when I dealt with this intrusion, there was no existing tooling for this. So, I had to write everything myself. Now I'm publishing this code so people don't have to do all this work again if they deal with PLT hooking. Okay, so who's evanescent bad? I call them putting the A back into APT. So APT, for those who don't know, it stands for Advanced Persistent Threat, which is mostly a marketing term because most of the targeted attacks that we look at aren't that advanced because these days you don't have to be very advanced to pop large organizations, right? But this actor is actually very advanced. It's like advanced nation state actor TM, so very interesting actor. And you can tell some of this by looking at the methods. So they do have source level access to the implant, so it's not like they buy a binary builder somewhere, but they actually have close access to the dev team, which is sometimes unusual depending on the country you're attributing this to. Like if you're looking at the US, they're not so closely integrated. You have the defense contractors that build stuff, and then you have the button pushers, the operators that actually deploy it, and there's not so tight integration sometimes. But this actor, they have a lot of additional capabilities ready off the shelf. You can see it like they snip a finger and you see another advanced thing depending on their operational environment. So they have like a huge stock of interesting capabilities to use. For example, in the specific intrusion operation, they initially just used the basic compiled version of the implant, and when they saw some people are starting to see their stuff and using strings to analyze this, they responded by just adding to the compilation process a GCC plugin that obfuscates all the strings, and that happened almost instantly when somebody started using the strings command. So they can adapt very quickly, and you just don't write a GCC plugin that works reliably within 1 hour. So those are all capabilities that they have, but they don't always bring their A game unless the defenders force them to bring their A game, right? And this specific actor has separate developer, A++ skills, and operator team. So it's like A-level team, which is still really, really good, but they're not as good as the developers, which is always the case because if you're really skilled, you're a developer, you're not an operator, right? So what is this toolkit that I'm talking about? It's basically an implant series that is designed to almost never touch the disk unless you tell it to touch the disk. So because we're looking at server compromises here, you don't actually need to do persistence across reboots because servers may be rebooted once a quarter or so, and if that happens, you can just recompromise it with the same ODA and then put your implant back in there. So it's very, very stealthy. You won't, normal typical disk forensics don't get you anything. You have to do memory forensics to see it at all. And even if you do memory forensics, that's very stealthy for that. So tries to avoid forensic traces as much as possible. I can't talk too much about finding this in the specific intrusion case, but even this was like pure luck that it was detected at all. Was like a slight operator fuck up. And looking at the, who we think is behind this, there's probably a lot of organizations and governments that have this shit running and just not see it. So that's also why I'm releasing this stuff. So yeah, looking a little bit more at their skills, the implant developers are highly skilled, really great stuff. When I reversed this, I thought, oh, you couldn't have done this any better. This is really cool shit. And if you look at a lot of targeted attacks, you don't often think that. So most of the stuff we reversed is like shitty stuff. But this one has really well done error handling and corner case handling. So they have binary compatibility to really old Linux versions. You can basically take the same binary and go to all kinds of distribution and it'll work instantly. And you can see that they are very, very familiar with like the Unix basics and the Linux ecosystem, so they really know their stuff really well. It's not like some other stuff that you see where people are familiar with Windows and then have to write something for Linux, but those people really understand everything there. And they know the whole toolchain as well, right? So they have a GCC plugin that scrubs local variables running out of scope, so they understand compiler design and how to write GCC plugins. Interestingly, they think overrunning stuff in memory with zeros is not sufficient, but instead they apply some more advanced patterns and stuff for scrubbing memory, which is interesting if you think about it for a while. They try to make sure it's not even overwritten with zeros, but even more advancedly scrubbed. Yeah, and also they have a GCC plugin to encrypt all global heap and global variables. So, you can't just use strings as, what I was just talking about before. The operator team is, well, the developers are highly skilled, the operators are skilled, otherwise they would be probably promoted to developers. They did some minor mistake, like you can see it's not the same people writing the code and using it because they did not properly adjust all framework configuration to the specific operation. Maybe they were just lazy, maybe the documentation wasn't as in-depth. So when you reverse engineer it, you find like options that they could have used or should have used that they didn't use, so they didn't use all the features to the maximum extent. And yeah, as I said, one operator one day made a slight mistake and ended up in a log file with one line, and this is how this whole thing was then detected. But if the operator didn't make the mistake, then this stuff is so stealthy that probably people wouldn't have seen it. Yeah, in terms of attribution, I'm not going to say too much here. If you really care about this, then you can get some more info from CrowdStrike directly. What I'm going to say, we have several low confidence indicators where this is coming from. A coding style and choice of specific encryption algorithms. So actually, interestingly, if you look at nation-state actors, they sometimes adhere to what would be the NIST in the US or GOST in Russia, for example. They adhere to these algorithm recommendations for encryption and so on. We can look at like who's benefiting from this intrusion, what target selection did they have, and also sub-target in the target. As I said, it was like IT organizations, right? And looking at C2 domains registration specific, so not saying like it's .ru, it must be Russia, but when has it been registered from where, in which language, and so on, right? For this specific intrusion, there's no conclusive operator activity times. So sometimes you see like people work to 9 to 5 in a British time zone, so it's probably GCHQ, right? But in this specific case, they were active 24/7 and they respond immediately to operational friction, right? So if somebody starts looking at their stuff with strings, takes them like 2 hours to deploy more obfuscated version. Which is also interesting because they don't always hit you with the hardest weapon they have. They gradually raise the level with what you're doing. And once they saw like, shit, this operation is really going down now, we're fucked, then they started just grabbing for credit card numbers to look like criminals who want to steal credit card data, but which is obviously like, some kind of red flag thing. And as I said, operator failures enable detection in the specific case. So yeah, it's always the operators who fuck up in the end, right? Okay, enough high-level blah blah. Let's get to some technical details. So the ELF format, what's the ELF format, what's our sections, what's sequence, and so on. So yeah, it starts with the name already, like, it's executable and linkable format. So if you think about it, they mix one file format both for the toolchain intermediates, which is like objects files for the linkers, and for the finished executables. It's the same file format, so you're already like, okay, these are different things, why is it one file format? And it gets messy with the name already, basically. So an ELF format has basically 2 types of data containers, and one is sections, which is basically the viewpoint of the toolchain, which is the linkable intermediaries. So one ELF file can have an arbitrary number of arbitrary named sections in the binary file with arbitrary content. So it's really like whatever container format. But the compiler and the linker, of course, then assign some meaning to these sections. So there's a text section, everybody knows text section does contain code. There's a data section, which obviously contains data. But this is really only meaning assigned to it by the compiler and the linker. So when actually people talk about the text section and executables, that's kind of like mixing stuff up because it's the code and the executable, but the sections is really something from the compiler toolchain, so that, you know, is mixing stuff up. And the whole section thing is, of course, file offset centric. So because the compiler works with files on disk, you know, it's easier for it to deal with offsets inside the file, so the sections are, you know, relative to the file start. And contrary to that, you have segments which are, you know, less understood, less known, which is the thing that the actual runtime loader uses and that the operating system uses to load your executable. They're much more coarse-grained, so you typically have, you know, only a couple of segments opposed to tens of sections. And they are mostly just grouped by the page permissions assigned to these segments, right? So in a typical modern executable, you have a read-execute segment, which will be your code, and you have a read-write segment, which will be your data, and so on, and will be extended to be your heap as well, basically. So you have only a couple of segments, and because this is used by the runtime loader, these things are address-centric, right? So basically, all the segment information is just an offset in memory based to the load base. So these are really, really two different points of viewing it, but they're mixed in this file format, and unfortunately, people mix them up when dealing with this file format, right? So if you look at it, as I said, you know, you have way less segments than sections, and the segments then also overlap multiple sections, right? So you have like the read execute and the read write segment, and there's a lot of sections in those, right? And that might be, you know, some different dynamic strings sections. There's a special section, you know, for dynamic loader info and so on, and the segments just covered it all. So it's very confusing. What's also interesting is that, you know, in terms of sections, some sections are at the end of file, and they're typically not spawned by segments. And because they're not overlapping with segments, that means that the dynamic loader will not load them into memory. So that tells you basically when an executable gets loaded into memory, you're losing some of the section data, right? Which is interesting, which makes it basically impossible to reconstruct the original ELF file after it has been loaded. So if you're dealing with memory dumps and trying to extract executables, you're always going to lose some data, which is different from Windows. On a Windows, a PE file is typically including all the headers, everything is in memory. So you know, when you're dealing with unpacking, you can dump the whole original unpacked file and even create a runnable executable in the simple packer cases from it again. So yeah. As I said, there's these PT load segments which describe stuff loaded into memory, and then there's some other special segments that tell the loader how to deal with this ELF binary during loading, so which is mostly descriptive stuff. And the segment headers and the ELF header, so they're really the file headers and the headers loaded, used by the loader, are typically part of the first PT load segment. So that means the main file header and the information about segments is loaded into memory. But the section headers, so the whole index of sections, is not part of the stuff that gets loaded into memory. So basically, if you're dealing with loaded ELF binaries, you can still work with segments, but you cannot work with sections anymore. And this is where the problems begin already, right? If you strip all section headers from an executable, you cannot link against it anymore, but you have still an executable that can be loaded by the operating system and that can execute. And since these section headers are at the end of the file, it's very, very easy to strip them. You just need to know the offset where the section headers start, and you truncate the file to the size, stripping off the section headers, and you'll have an executable that can still be run. So there's like, you know, one line of bash stuff, bash magic that you can use to truncate them, and it will still run. But most of the analysis tools will actually fail to parse any data from it now, like object dump, readof, and so on will tell you, no, it's a broken file, but the operating system will load it. So with this simple line of bash, you can already get rid of all the existing analysis tools. And the short thing is basically you shouldn't be relying on section information for parsing ELF executables in your tools. But you know, people are lazy. Sections are nice to parse because sections are file offsets, right? So if you write a tool that is supposed to analyze ELF files, then you just use the sections because you don't need to convert the memory addresses back to file offsets. So people always use sections, and yeah, easy to thwart. So yeah, basically what tools break? Object dump, read ELF, all the binOtil stuff breaks. PyELF tools, which is a kind of famous library for dealing with ELF binaries in Python, also almost purely relies on section headers and breaks. IDA Pro breaks to a certain extent. It can still, you know, load the segments, but the whole dynamic symbol stuff breaks, so you don't know actually which libc functions are being called and so on. And well, I'm going to stop the list here, but basically all the tools out there break. So that was the first problem I had, because I dumped the executables from memory, and I didn't have any files because it doesn't touch the disk. Yeah, I didn't have any tools to analyze stuff anymore, which is kind of hard. So I talked about this problem on Twitter to some people and on IRC, and everybody was like, yeah, we know these problems, and it seems like everybody seems to have something private. Or not everybody, but most of the people I talked to are like, yeah, I have some tool, but the code's so ugly, and I will not publish this. Recently, actually, Ryan O'Neill, or also known as Elfmaster, made this site like BitLakeCase, where he said like, oh, in the last couple of 10 years or so, I've written so much code, never published, I will not publish all my code. The only code he did not publish was the one that would be interesting for me, which is some Dapper CFT thing, which is called VMA Voodoo, which is kind of like a ELF antivirus thing that can actually detect PLT hooks in memory, so it's exactly what I would like to. But he didn't release it, so I talked to him, and he says it's definitely not going to be published before May this year, and probably not afterwards, because, I don't know, DoD is interested in it and whatnot, so yeah. And of course, your favorite AV will surely have a Linux scanner, and I'm really sure that the AVs really do a good job and will support scanning for this in the future, right? Yeah. So why do we care about this? The PLT hooks, obviously, from the intrusion. But let's talk about first, to understand this, how the runtime dynamic linker links your images in memory, because you have all these different ELF libraries that need to call into each other. How does that work? And in other words, how does the dynamic linker scramble and break your binaries during loading, right? Okay, so first of all, very, very old school, you can do statically linked binaries. So you have all the code that the binary is using. It's just getting all linked at compile time into one giant executable that contains all the dependencies. And then all the linker needs to be, or all the operating system needs to be is just map the code into memory, which is basically parsing the segment headers, creating the memory mappings, loading the contents, and then you can just, fire and go. And you don't need to do much. So because it sucks if every of your executables pulls all the dependencies into one file, you have a lot of duplicated memory and disk space and so on. So they invented dynamic linking, which makes sense, right? So you have all these libraries. They are just separate things on the disk, and once a process depends on the library, it just gets selectively loaded into the process and then put together. So interestingly, dynamic linked executables are not really the executables that get executed. So in the Linux terminology, ld.so is the actual executable that is the main executable in any dynamically linked process. So when you think you run you know bash scripts, right, which have a shebang. So when you execute a bash script, you actually execute bash, and which then interprets the bash script for you because it's an interpreter. And this is the same kind of thing for LDSO, for dynamically linked things. LDSO is an interpreter, so it's actually statically linked executable that then will load your executable and interpret the dependencies for you. So the kernel parses the program headers and maps the memory for you, but the whole process of linking then happens in user space. So all the dynamic linker does is, of course, only resolving the symbols in memory, but yeah, has a big task on its own. So how does it work? If these section headers are not mapped into memory, right? How do you, because the symbols, your dependencies, your dynamic dependencies are a section, and if you don't have the information about the section headers, you don't know where the section is. Well, this is where a special segment comes in. It's called the PT dynamic segment type, so you can have multiple, but you never have multiple because only one makes sense. And it's a segment that is just there for the dynamic linker, and it's basically like tag value kind of structure. So it's always numeric tags that tell you what kind of information is it, and then the value is typically a pointer into the memory. And this is already where it gets very messy, because the segment headers are memory addresses, and then this is a segment again full of pointers or relative pointers to the image load base. And this is why it's nasty to parse it this way if you're dealing with disk files, because all these memory pointers, they're not equivalent to file offsets, so you need to translate this first, right? So you have these tag and value pairs of native pointer size, so it's always like 2 pointers per pair, and it's a table, and this is just kind of null terminated. And And it has all these pointers to interesting stuff like a string table, which is then used for the names of the symbols that you want to import, a symbol table that contains the list of symbols that's imported. All the relocation information is in there, dependencies, like which libraries actually do need to be loaded, and so on. And all the information is available through the special segment. So all you need, you can get over this way. But as I said, it's like kind of messy to deal with this for files. And yeah, that's why tools use that, right? So the other thing with this header is during loading, the dynamic linker uses the special segment as kind of a scratch pad. So after a binary has been loaded, the segment doesn't look anymore like it looked on disk because basically the dynamic linker will add the image load address, the base address to all of the pointers to basically just have a pointer in there and so on. So you need to first read the linker code to understand how to reverse the modifications it does to the segment to get to the original segment. So you can translate it back to file offsets, right? And then there's the PLT, which is the PLT hook thing I was talking about, right? The procedure linkage table. So it actually, when people talk about the PLT or the global offset table, these are actually logical concepts that exist as sections and are concepts from the whole compiler tool chain. But it's not like really part of the ELF file format specification, and it's not part of the linker logic. So if you look at the Windows file format, the portable executables, they have an import address table, which is part of the actual file specification and is well defined. The PLT actually is implemented depending on your toolchain in different ways. So GGC and LLVM all have some kind of PLT, but how you implement it within the boundaries of the ELF specification is up to the toolchain. So for GCC, which is the case I'm going to talk about here, imported functions are always this small stub, which is like jump, and then they dereference the PLT memory, right? So there's a certain offset in the PLT which represents a function pointer to the actually imported function, and then there's this small stub, right? And on x86, this is called jump rel, because they're always relocatable jumps. So instead of using some specific thing which tells the linker put a function pointer here, they use relocations, at least in GCC, these jump rel relocations to implement the PLT concept. So it's basically, initially the PLT is zero initialized, and then they tell it, okay, for every slot in the PLT, they have one relocation information which is relative to a symbol. And then because you want to call the actual symbol, there's like a zero offset. So this is like really, really convoluted way of implementing these imports. So they have the PLT, which is this table of imports, but they don't have like a direct mapping to imports, but there's this long list of relocations that tells you like, okay, this is the PLT slot. Now I want you to fill this PLT slot with the address of the symbol plus a zero offset. And this is like the huge ELF overhead for just implementing PLTs. And then even more complicatedly, modern compilers mostly use lazy linking. So instead of the dynamic linker resolving all the symbols at load time, there is not a zero function pointer in there, but actually it's a function pointer to a small stub that then tells the linker, please propagate this relocation. So before a function has been called for the first time, it will actually be pointing to the small stub. So the interesting thing about this is then actually when you look at an ELF executable dump from memory, you can tell which functions have been called and which haven't been called already. But yeah, as you can understand, maybe it's really, really complicated when looking at something loaded into memory to figure out, without the section headers, what PLT slot corresponds to what symbol, and thereby what call in the original binary actually calls which API, right? And to make it more messy, looking at the memory dump, of course, there can be code that actually hooks a PLT. So hooking in generally just means like you want to redirect a function call to a specific function to an arbitrary, interception point for use to change arguments, add additional behavior, I don't know, maybe stop the function call and so on. And if you typically do hooking, it's maybe you need a disassembler engine to disassemble the original code, inject your jump to your code in there, and so on. But if you actually just want to hook exported API calls from the call side, you can do it a lot easier because these jump rel slots in the PLT, they're just function pointers, right? And replacing a function pointer with the address of your own hooking function and then calling the original function is a lot easier to do this, right? So the challenge, of course, if you implement this, is locating the proper jump rail slots to hook. Unless, of course, you do LD preload-based hooking, then you can just, export the symbols you want to hook, and then the linker does the whole hooking for you. But LD preload, of course, has the disadvantages that you need to provide this information before the actual starting of the process, right? You cannot use LD preload on a running process. And in the intrusion I'm talking about here, they injected into running processes from the post-exploitation shellcode. So, you have the exploit, and then they inject into running processes to never touch the disk, right? So, yeah, they have to implement the whole dynamic linking logic inside their framework. And as I said, this one really handles all the corner cases for the different tool chains, which is really nice, right? I just talked about the jump rail-based PLTs, but different tool chains, there's two other ways to actually implement PLTs within the ELF file formats constraints, which is done by all the GCC versions and so on. And this is pretty fascinating because this tool chain I reversed there really supported GCC 2.x kind of PLTs and so on, which is they have binary compatibility to a lot of old machines as well. And yeah, because it's enforced by the ABI to have this kind of relocation support and so on, it's a very generic technique, so you're not really dependent on any tool chain if you handle all the cases. And even though it's very convoluted to deal with all this dynamic linking, it's probably still easier than inline hooking, where you have to do some disassembly and so on, right? Okay, so that's PLT hooking and what I did. So yeah, I'm looking at this. I'm getting these memory dumps, and I have no existing tools that can handle these ELF file formats. I have nothing that can deal with PLT hooks because, there's Volatility, which is really great, but for Linux, they basically, or mostly, had only kernel support because all the cool kits use kernel rootkits, right? Unless you're a really advanced actor who wants to stay under the radar and you're just staying in user space. And the other, of course, advantage of using PLT hooking opposed to a kernel rootkit is that you have way more binary compatibility, right? If you want to deal with kernels, you have to support 2.6x, maybe even 2.4, so their stuff even works on 2.4 kernels and so on. And if you just have this user space stuff, you're way more portable. So may sound not as sexy as your own kernel rootkit, but then again, if you're really want to get to your goals, you don't have to be sexy, but you have to be effective. And I think the user space stuff is the more effective stuff. So in a way, it's more advanced or more real world. So yeah, I wrote a volatility plugin to detect PLT hooks in volatility dumps. This is a story how to false positive, which I will explain in the demo a little bit more, because turns out even on a Debian 6 or Debian 7 default install, you'll have a bunch of PLT hooks. So it's kind of like a problem. Yeah, so what is volatility for those who don't know it yet? Volatility is basically a Python program that lets you analyze full memory dumps, right? So not from a single process, but from the entire physical memory. They had it originally for Windows because Windows is the thing people care about, right? And then later they added OS X and Linux support. And as I said, for Linux they only look at the kernel because only noobs do user space stuff, right? So yeah, it's very nicely done though. It's plugin centric, so everybody can write additional plugins or modules to implement new commands. Which was useful for me. So I actually implemented two modules. One is called Linux ELFs, which just scans the whole user space mappings for ELF binaries using the ELF magic signature, and then using this PyELF tools binary I was talking about earlier, which is broken. So I also patched PyELF tools to support loaded images and to support segment-based information opposed to sections. And that's already really useful because volatility by default only lets you dump the memory mappings, but typically an ELF binary spans multiple mappings, so it's useful to see what mappings corresponds to what binary and so on. And then there's another one, of course, Linux PLT hook, which scans all these ELF binaries that you have in a process for the presence of PLT hooks. Okay, so how do we define a PLT hook? And for our sake. So the PLT always contains function pointers to other modules because you import functions from other modules. And it's not sorted by modules, so even if you group by modules and see if it isn't in the right order, something that doesn't help. The jump rail relocation just specifies a symbol name, but not from which module the symbol name needs to be imported, which is kind of messy. So if you have multiple modules, that export the same symbol. There's no formally defined logic which symbol to take. And also means that if you import a symbol and you don't tell the linker to import that module, but something else imports that module, it'll still work. So it's easy to break, and people often experience that they run programs which link fine, and then at runtime they figure out there's a symbol missing, right? So how can we distinguish a hook from a legitimate import? Because we have no formal specifics where this should be imported from. At least there's these special dynamic tags that are called needed. So it's a list of required or to be loaded dynamic dependencies. And a library should list all libraries it's importing symbols from. So you can actually run, right? Because you need the symbols. So the heuristic that I'm using is build a transitive full of these DT needed dependencies and check if the jump rel pointers actually point into any such module, right? Because if I say import something from MySQL and then this in turn depends on libc, it's legitimate for my module to still be depending on libc. So it's broader than you would initially think, but it's still sufficient for detecting PLT hooks mostly because if you have anything ROC injected or like LD preloaded, then it's unlikely that the main executable legitimately depends on these things. Yeah, so DT needed is actually how does the toolchain know which libraries are needed? Well, you have these -L compiler switches. And this basically then ends up in the executables. So yeah, symbols can be imported from main executables, but also from any other module. And if it's not present, it's a linker error. But some applications have a horrible build process and are linked in a weird way. And so one example, not to bash on them, it's just one example. Apache 2 modules. They always implicitly link against this Apache plugin library. So Apache modules know this library will be loaded into Apache, but all the module SOs do not specifically say like, hey, I depend on the specific library. They just assume the symbols will be there, and they are magically there. But that means that this library is not in their dependency list, which means it will generate a false positive in these heuristics because their build process is broken. And there's nothing you can do about it because yeah, you don't know generically how this should be. And then a real system has some legitimate PLT hooks, which are mostly usually due to LD preload libraries. So there's this libnpm_compat, which, as I said, in Debian, for example, the initrd does some UID shadow emulation and so on for the initrd, and they have this libnpm_compat library which does that. And it's loaded by LD preload for everything spawned from the initrd. So, and of course, some processes will survive the boot process. And yeah, bash actually redirects malloc and the other heap functions to the main executable to use their own heap allocator. So there's a bunch of things that you'll always see in anything. So yeah, I added a whitelist switch to ignore certain mappings in the output, but that's basically like expert input, right? So you have to use a whitelist hashes of binaries that you want to ignore because they are verified good or something. Otherwise, these hooks will still be outputted because they are PLT hooks for real, but they have legitimate reason to be there. All right, so that's all the problems, blah, blah. This is actually a dump from the main thing, right? So, as you can see in the original intrusion, you have EVP cipher in it being hooked here. EVP cipher itself, PAM is hooked, so some nasty stuff that they were doing on those servers. Yeah, so because I can hardly demo the original memory binaries here for you guys, I prepared another demo. Oh, let's hope this works. No, yeah, a little bit, still hard to type, I guess. This is probably why you prepare demo videos, which I didn't do. Okay, so you can see it here. What you can see here now is like just VMware with a Debian 6 thing, and Volatility is awesome enough to support VMware memory snapshots directly. So let me just spawn a process here. Cat is a nice example because it blocks, and now I'll suspend to get an actual memory snapshot. Can you still understand me if I talk a little bit in this direction? Okay. So at least I prepared the command lines here. All right. Great. So my window doesn't fit on the full screen. So the first plugin I'm running on this memory snapshot now is like this Linux Elf thing. So for some reason, volatility on Windows is really, really slow for me. It's a lot faster on Linux actually, but yeah. So you can see all the different PIDs up here. Maybe I should show the table header. Right? So you have the different tasks. You have the actual extents of the ELF image, which is different from mappings because it starts at the mapping base, but the image doesn't always extend to the end of the actual mapping. So you can see the ELF file name. So libraries, they have in their dynamic tags, they have like a file name that tells you like this library is actually this file name in the dependency chain. Main executables typically don't have these fixed names, so in that case it's just outputting the full path on the disk. So you can distinguish this basically, if it starts with a slash, it's a full path, otherwise it's what the binary claims to be. And then of course you have the dependency list. So if you want to play, it's really nice to use .den to do like dependency graphs, what library or what processes depends on what and so on. But yeah, that's just the ELF scanning. All right, so this is an existing command. PS list just gives you a list of running processes from the memory dump. Okay, so we have our cat down here, and this is the PID of cat. So I will just now selectively run the PLT hook command for that PID. And it should be a little bit faster, because it's just one process, right? Okay, and here you can see what I was saying earlier, right? There's always some stuff that looks like PLT hooks in legitimate binaries. So even CAD has hooks, and that's mainly because the linker, the dynamic linker, uses the heap as well. But the linker itself doesn't say so, because it implicitly, the dynamic linker implicitly assumes libc will be there, so it just has these symbols without specifying them. So you see some linker stuff importing from libc. So as I said, as an expert input, it always makes sense to write with libc, for example. All right. So let me resume my snapshot here. Yeah, I'm not going to use the super advanced stuff from the extrusion. Instead, I'm just going to use some LD preload thing I found on GitHub. So I just went to GitHub and searched for LD preload, and yay, there was like something. So I'm just going to use this hooking library now and run cat again. So you can actually see this is a nice hooking library which outputs the hooked calls. So it hooks malloc and read and so on. So I'll suspend the machine again to create a memory snapshot. And then, of course, we have a different PID, so let's list the processes first again. All right, and then let's look in this new PID for PLT hooks. Okay, and now we can see it. So the actual bin cat binary, the symbol read and malloc have been hooked. And the hook, this is the address of the hook, and this is actually the binary that provides a specific hook. So it works, yay. Thank you. Yeah, if stuff works directly, it doesn't look that hard, does it? But it was painful. Yeah, so anyway, it's all open source, yay, but we all know open source doesn't really work that well. How can you get the code? Well, so initially I wanted to have both patches, so as I said, I needed to patch the library that passes elves, and I needed to patch volatility, so I just wanted to get them upstream. For PyElf tools, it's scheduled to be merged upstream at some point. Guys just too busy to merge it in right now. So thanks to Eli Bendersky for writing PyElf tools in the first place, and now everybody sent him emails to merge the patch. For volatility, it initially was scheduled to be merged into upstream into summer, so merging is apparently very hard, but then, this, can you read this? So I asked like Andrew Case, did you get my patch? And he was like, yes, we rewrote it because we don't like the F parser you're using, so they're rewriting everything, and they're holding it back though until they're publishing their book to promote the book. So yeah, 2 cases, 2 open source projects, 2 upstream patches proposed, 2 not merged upstream. So I'll just be putting them on my GitHub. At some point, I can't access GitHub from Asia, really, with this laptop, because I don't have the creds. So you can watch my Twitter until I do that. And for now, you can actually use this URL there to download like a tarball, because I hate presentations, like my presentation last year that come without code. So this year it comes with code. And I'll tweet that link in a bit too, so you can actually download it today and start breaking it today.
Do you familiar with the RESI work, RESI project?
RESI, no.
E-R-E-S-I.
No.
Okay, so this like big project which has been rolling since 2004, I believe, yes. And there is this kind of research similar to yours plus more.
Okay.
That's the reason I'm asking. So, okay, if you are not familiar.
Yeah, okay, would have good to know before I start writing my own code. To solve these problems, but does it support volatility or like memory dumps, or it's just for core dumps, or?
So this utility it's a big framework. There is own language, which calls RESI itself, which was designed for reverse engineering and playing with the ELF binaries itself. There is a lot of talks about that. In the 2007, there was a talk in the Black Hat. Julian Vanille was the owner of this project, apparently, and yeah, mostly it operates on the ELF itself, not on the dumps, but ELFs, and it does detect not only the PLT hooks, but just manipulate with everything, and it's scriptable, so we can write in the high-level language this kind of detection also.
Cool.
Okay.
So if you can give me that, I'll add it to the references. Thank you.
So it looks that you basically extracted the data structures that were left over by the loader, so the PLT and GOP PLT and stuff like that, but the loader has a lot of other internal data structures that you could use for some more details, how the library actually ended up in there. Do you look at those as well, or is it just the libraries themselves?
So, I mean, for the specific intrusion, that would have been useless because they inject with ptrace and even inject the PLT hooks with ptrace. So there's no trace in the dynamic loader structure.
Which would be a nice indicator, right? If it's not in the loader data structures, but in the PLT, you're pretty sure that it was malicious.
Right. That's another heuristic. Problem with that is that you're then depending on specific dynamic loader versions. And their framework is very generic, and volatility is very generic, so I try to be as generic as possible with detecting it as well. So you could certainly test for certain loader dynamic linker versions and add additional heuristics, but I didn't do that yet.
Or just extract the header files from the dev machine.
Yeah, of course. If you have source access, you can automate this, yeah.
Hello. I was looking at you when you're talking about hijacking or inserting code in the PLT section. Have you considered another section, for example, constructor and destructors of the ELF file format?
No, so I only looked at the PLT because the thing is these specific implants, they use PLT hooking to hook certain special APIs, right? For example, they hook some PAM APIs to add additional authentication successes, basically. So hooking into the constructor gives you like initial code execution, but as I said, like this stuff, and this not only this specific case, but I mean the family of techniques I was targeting is about like injecting stuff, injecting hooks after load time, right? And constructors and destructors are just for getting code execution, so to say, like for ELF infections. So I could certainly add that because it's not hard to do and maybe interesting, but I didn't for the specific format. Also, to be honest, I think, again, if you have section headers, finding constructors and destructors is really easy because they have their own section. Yeah. For the segment-based information, I actually have to look into how the dynamic loader finds these things. It's probably a little bit harder, but yeah, it's something to consider. Cool, thanks.
Thank you.